So these are the slides, reductions to the halting problem. And you'll see I used to cover a lot more, various hard things. And what we're going to cover up to the purple line is what I covered the last few years. And it's just quick reductions and just a little thought about some harder ones. Now, you guys are better experts at reductions now because we did them for NP. So let's consider a computational problem. Let's call it P sub high. The input to it is a Turing machine, the description of a Turing machine in an input. And the answer is yes, if when you run that Turing machine on that input, at some point during the computation, it outputs the word high. All right, so that's a computational problem, right? And the goal is to prove that this problem is undecidable. The goal is to prove that there's no algorithm which can always get the right answer to this problem, right? And so there's various steps to doing this, and the goal here is to not have people panic. Hello, Ariana, how are you doing?
Hi, I'm good. How are you?
See, she's another one who I recognize. She might even be the one I recognize the most.
Oh, thank you.
All right. So, and we know that she doesn't have a cat.
No, I have a dog.
She has a dog. All right. So the key here is to understand each of these steps without panicking. All right. And what I find people do is, in all courses, is they think about other things that they want to panic about, and they think about, oh, how does this happen and how did this happen? And really, the best plan is you just think about each step one at a time and not try to worry about solving the world's problems. All right, so first, what's our overview is you've had on the test. It was, right, so there's some statement, not A. The statement not A is that P halting is uncomputable. All right, we know that already, right? We proved that already in a previous class that the halting problem is uncomputable, and I'm calling that not A. Another statement is that the P high problem is uncomputable, right? And that's what we want to prove, right? So what we have to prove is that if not A is true, then not B is true, right? But it's hard to talk about there not being algorithms for things, right? It's easier to prove that there is an algorithm than to prove that there's not an algorithm, right? Because to prove there is an algorithm, what you do is you construct an algorithm, right? So what we're going to do is we're going to do the contrapositive of this. Instead of proving not A gives me not B, we're going to prove that B gives me A. So how do we do that? Well, what is B? B is the state that P high is computable, right? It's kind of like we're proving it by contradiction. We want to prove that P high is not computable. So by way of contradiction, let's assume it is computable, right? Well, if it's computable, then we have an algorithm for it. And we can use that algorithm. We're going to call it an oracle because it's something that we're assuming that exists, that's powerful. And we're going to use that to design an algorithm for the halting problem, right? So we're going to actually write code to solve the halting problem, all right? But it won't be code all by itself. It's going to use the oracle for the high problem as a subroutine, right? And that will prove that P halting is computable, right? But which will prove A, because that's what A is that it's computable, right? But the thing is, we know that the halting problem is not computable, right? So that means P high is not computable. Does everybody get this picture? Right? It's the same as what we did and before with the card problem and the SAT problem, but there we were down levels. The question is there a polytime algorithm for it or not, right? Now we're asking, is it computable or not, right? Same idea, different height in the complexity hierarchy, right? So now that's our goal. And the way we write that was we say that the one problem, the high problem is at least as hard as the halting problem. Or we say the halting problem is no harder than the high problem. Why? Because if you can solve the high problem, you can solve the halting problem, right? All right, so what we have is an oracle to solve the high problem. And like we did before, well, actually maybe not. Before I might have had the oracle guy in there, right? The burning bush. But now I have my oracle being Einstein, right? And what does Einstein do for me? You give him the description of a Turing machine and an input, and he'll tell you maybe yes, that M does say hi, or maybe he'll say no, M halts without saying hi, or maybe he'll say, hey, M doesn't ever halt, but even though it runs forever, it still never says hi. So he'll say no, right? So in these two cases, he says no, because maybe it halts and doesn't say hi. Maybe it runs it forever and doesn't say hi, but it never says hi, right? So he says no. If M might say hi and run forever, and M might say hi and halt. It doesn't matter. Either way, if it says hi, then he says yes. Everybody understand what the oracle does? Oh, there's our oracle as a burning bush. All right, so now what is our goal is design an algorithm for the halting problem. What is the halting problem? Is you give it a Turing machine and an input, and it tells you whether or not M halts on I, right? So what do we need to do? Well, we need to do an instant map, all right? Over here, we are given an input to the halting problem, right? And what we give to the oracle is an input to the halting problem. No, to the high problem, right? So we have to take the input to the halting problem, and we have to produce an input for the high problem. So here, what's the input to the halting problem? It's a Turing machine, and we care, does it ever get to the halt state, right? And what we have to do is we have to produce a new Turing machine, right? So here's our M prime. How are we going to build our M prime? Is we're going to take our Turing machine M, and we're going to copy it, right? An exact copy of the Turing machine, except we're going to make a small change to it. When M goes to the halt state, what is M prime going to do? Right? What is M? What's our question about M? Our question about M is, does it halt, right? That's what we want to know about M. So what we want to know about M is, does it ever get to the halt state? What does the oracle tell us about M prime? Anybody remember? What does the oracle tell us?
That it works.
That what? What was our problem? Let's go back to our oracle. Remember? Our oracle, we give it an M prime, and it tells us whether or not it says hi. Right? That's what it tells us. It tells us whether or not it says hi.
So we replace halt with hi?
Exactly. Exactly. So what we care about is, do we get to the state? So what we do is replace the halt state with a high state. So if you ever get to this state here, what does the Turing machine do? It says hi, right? we make sure that nowhere else in the Turing machine does it say hi, right? This Turing machine is going to say hi if and only if it gets to the high state. And what about M? Well, M's going to halt if and only if it gets to the halt state, right? So this Turing machine is going to say hi if and only if this Turing machine halts, right? Does that make sense? Right? So so let's think about what happens, right? If M halts in the halt state, then M prime says hi in the high state, right? So what we're saying is if Mi halts, if and only if M prime I says hi, right? So now I could also I could describe the Turing machine in terms of its states, but sometimes, you've all written Turing machine code. It's a pain in the butt sometimes to write Turing machine code. So sometimes we can write pseudocode for it. So here I pretend I've been given code for M, the Turing machine for M. And what I'm doing here is I'm writing pseudocode for M prime, right? M prime is going to be a Turing machine, and I'm telling you what it does. Well, what M prime, it's given some input I, and what it does is it simulates M on I, right? We know what M is, right? So we just, we do the same things that M does on I. That's what M prime does. It does exactly what M does on I. And then when M finishes being on I, what does M do? When M finishes, it goes to the halt state, right? That's what M does when it finishes. And at that point, what do? Well, we don't halt at that point. Instead, what we do at that point is we say hi. After we say hi, we can stop or we can not stop. I don't care. But that's what it does. It says hi, right? Everybody see that this is code for this Turing machine, right? All right, so now here I'm going to add a little nuance to it. I'm going to add the little extra statement. Make sure that when you run on M on I, it never says hi. All right? So I'm going to just, to make sure it doesn't say hi, I'm going to suppress any output it gives. That just assures me that M prime doesn't say hi until I want it to say hi. Right? All right, so now I need to design an algorithm for the halting problem. Okay, I start building my algorithm. What does my algorithm do? It's given an input M and an I, and it has this oracle that solves the halting problem. So what we do is we produce M prime, right? I told you how do we produce M prime. It's basically the same Turing machine without the halting state and with the high state added, right? So this is our M prime as we described. And we give that M prime, and we give the same I too. It might as well give it the same I, it doesn't matter, right? And then what does the oracle tell us? It tells us yes or no. Either M prime says hi or M prime doesn't say hi. And then what do? We give the same answer, yes or no. Right? Does that make sense? So now that's their algorithm, right? Now we have to prove that the algorithm solves the halting problem. How do we do that? Well, we have to prove that if M and I halts, then what? If M and I halts, then we proved already if M and I halts, then M prime and I says hi. That's an if and only if, right? That's how we design M prime so that it says hi if and only if M and I halts, right? And if an M and I halts, then what happens? Then the oracle says yes, right? The oracle says yes if and only if M prime says hi, right? That's what the oracle's job is. And what about our algorithm? Well, our algorithm says yes if and only if the oracle says yes. right? That's the definition of our algorithm, right? We say yes if and only if the oracle says yes, right? There, look it. Now that proves that the algorithm works. Why? Because the algorithm says yes if and only if the answer is yes, right? And that's it. That's it, guys. We're done. Was that hard? That wasn't so hard, was it?
No, it wasn't.
All right, good. All right, so what is our conclusion? Our conclusion was we've already shown that not halting is uncomputable. And our goal is to prove that high is uncomputable, right? So we showed that if high was computable, then we could design an algorithm for the halting problem, but we can't design an algorithm for the halting problem, so we can't design an algorithm for the high problem, right? Everybody got that?
Yes, sir.
Yeah.
Excellent. That wasn't so bad. Okay. So we're going to do some, as I said, we're going to do a list of easier problems, and you know that these could get really hard. And I've on the test in the past given ones that were a little harder than the ones I gave in class, and you know that not very many people were able to do it. So what we're going to do is we're going to try to give some easy ones in class, and then I'll try to think of an easy one to give you for the test. All right? So here's ones we're going to do. We already know the halting problem. Does M halt on I? We could also ask, I give you a Java program. Does the Java program halt on I? Right? Well, you know that's equally hard because we can convert from Java programs to Turing machines, no problem, right? We could also have all these other various types of programming languages that you haven't learned about. Primitive recursive programs, they always halt. Uniform circuits always halt. Humans always die. All right, so we know those problems are easy because the answer is always yes, they do halt. All right, what are our other problems? We want to show that does M say hi, that it's uncomputable. Well, we did that already, right? Does M halt, is it something special about the input? No. Does M halt on the empty string? That's also undecidable. I give you a Turing machine and I want to know, does it halt on the empty string? Here, I give you a Turing machine, does it halt on every input? Or is there some input on which it runs forever, right? I give you an M, I ask, does there exist an input on which it halts, right? Or I could give you two Turing machines and I ask, do they give the same answer on every input, right? These clearly are hard problems, right? Here, this is the one that kills students the most, all right? I want to know, it's even the question itself makes people scared, all right? I give you a Turing machine. I want to know something about the language that the Turing machine accepts, right? Some inputs, the Turing machine is going to give yeses for or halt for, and some of the inputs the Turing machine is not going to halt for, right? So that forms a language, right? The language of inputs for which this Turing machine halts for, right? The question is there a regular expression that expresses that, right? It's a question. It's hard to prove, all right? Another question is I could give you a fixed Turing machine. Turing machine's scary. And the problem is I give you an input and I want to know, does this scary Turing machine halt on my input, right? There's another problem. These are all undecidable problems, right? And so here's more generic. This is what we call Rice's theorem. I give you a Turing machine and I want to know something about what the Turing machine does, right? I don't care how it does it. I want to know something about what it does, and that's undecidable, right? Now, here's another problem which gets into a little more complication. This is the problem. I give you a Turing machine and I say if it does halt. Here's another problem. I give you a Turing machine and I say yes if it doesn't halt. And we could get into whole nuances between this type of problem and this type of problem, acceptable versus co-acceptable. And I'm just telling you that that is an issue, but we're not going to spend hardly any time on it at all, because it's just another whole nightmare that's not worth getting into. All right? So we're going to prove that all of these problems are undecidable. This one here is the one I gave a little star because we use a different Turing machine. Remember, a different reduction. Remember, our reductions were if the oracle says yes, we say yes. But to prove this is undecidable, you have to switch the yes answers and the no answers, which is different between decidable, recognizable, co-recognizable, all these various issues that we don't want to get into too much. All right. So this is just the word decidable versus recognizable. I'm going to just tell you once what the definition is, and we're not going to care too much about it. Oh, we actually covered it when we were doing those logic slides. All right. Remember, a problem is decidable if there's a Turing machine that on yes instances halt and say yes, and on no instances halt and say no. So in every instance, they have to halt, right? Well, recognizable are Turing machines that on yes instances halt and say yes, and on no instances, well, they could do anything but that. They can halt and say no, or they could run forever. I don't care which, right? And the thing is that the halting problem lives up here, right? We say the halting problem can't be decided, but the halting problem can be recognized. Why? Because you given me a Turing machine and an input, I just run it, right? If it's a yes instance, it halts and I can say yes, it halts. But if the Turing machine runs forever, then I don't know then I will never halt, right? Because I'm simulating it. Anyway, that's just saying the halting problem lives there. The not halting problem lives there. So do we care about all those problems live up there? Other problems live up there. And we're not going to care about all that. All right? We just care, is it decidable or not? All right, our reductions. So here is the set. We want to prove that one problem is harder than the other problem, right? Here our harder problem was the halting problem, and the easier problem was the high problem, right? So, oh no, it's the other way. See, one way it's easy to get wrong is you do the reductions in the other wrong direction. We want to prove that the halting problem is easier, right? If we can solve the halting problem, then we can solve the high problem. So we pretend we have an input to the halting problem. So here, this is the input to the halting problem, right? And remember what we did is, right, we want an algorithm that differentiates between, oh, right, and here's the easy problem and here's the hard problem. And they have different types of inputs, right? In this case, both problems were given a Turing machine and a description of a Turing machine. But it could be one of them is given an elephant, and we want to know, is the elephant pink? So they could be different types of inputs. So this is the input to the easier problem. This is the input to the harder problem, right? But each problem is a yes/no problem, right? So we're given an input, and we want to know, is it a yes instance or is it a no instance? All right. And so what are we given is we're given an oracle that can solve the harder problem, right? You give it an input to the harder problem, and it tells you whether the input is a yes instance or a no instance. And what do we want to do is we want to come up with an algorithm for the easier problem. We're given an input to the easier problem, and we want to say yes or no, whether the input's a yes instance or a no instance, right? And that's how we design that the one algorithm is harder than the other, right? And so it's hard to prove that the hard problem is hard, right? So it's easier to prove that the easy problem is easy. And how do you decide it's easy? You prove it's easy by coming up with an algorithm for it, right? And when you design the algorithm for it, you use the algorithm for the harder problem as a subroutine. All right? So we pretend that we have an algorithm that solves this harder problem, and we use it to come up with an algorithm that solves the easier problem. All right? So here, that's our oracle. Our oracle is this guy who solves the harder problem, right? And now our goal is to build an algorithm that solves the easier problem, right? So what is our algorithm for the easier problem going to do? Well, we're given an input. Here I'm calling it the algorithm problem. Before it was the easier problem. Now it's the problem for which I have an algorithm for. And this is the problem for which I have an oracle for, right? I'm designing an algorithm for this problem, right? So I'm designing an algorithm for the algorithm problem. I'm given an input to it. What do I do the input to it? I don't know whether it's a yes instance or a no instance, right? That's why I got rid of the circle, right? All I know is that it's an input. And I take this input to the algorithm problem, and I'm going to map it over to an input to the oracle problem. So I decide a function that takes an input to this problem and produces an input to that problem, right? So that's my oracle, my instance map, right? Does that make sense? And what do I do with this input to the, right? Now I'm given, right? This gives me an input to the oracle problem. And what do I do for it? Clearly, I give it to the oracle, right? And what does the oracle do? It says yes or no, right? I give the oracle, and the oracle tells me yes or no, right? And what do I answer? I give the same answer. If the oracle says yes, I say yes. If the oracle says no, I say no, right? So what do we need for this algorithm to work, right? We need that the instance map preserves the answer. What we need is that the instance map maps yes instances to yes instances, and it maps no instances to no instances, right? Even though we don't know whether it's a yes instance or a no instance, right? What did we do before? We were given a Turing machine that had a halting state, and we mapped it over to a Turing machine that had a say hi state. Do we know it halts? No, we don't know if it halts or not. We don't know if it says hi or not. We just do this mapping. All right? So what do we have to prove? We have to prove that this input to the algorithm problem is a yes instance if and only if the input to the oracle is a yes instance, right? Because that will tell us, right? That's what we have to prove. Because we know the oracle is going to say yes if and only if it's a yes instance, and we know our algorithm is going to say yes if and only if the oracle says yes, right? So this is the only piece we have to prove. All right, now let me give you code for my algorithm. This is exactly what I said before. It's code for the algorithm problem. I'm given an input to the algorithm problem, right? That's the precondition, is I'm given an input to the algorithm problem. And what is my goal? My postcondition is that I know whether or not it's a yes instance for the algorithm problem. And what do? I put it through the instant map, and I get an input to the oracle problem. What do I do with that input? I give it to the oracle. The oracle gives me some answer. What's my answer? It's the same answer. I return my answer.
So
Yeah?
for the input, it could be like integer or it could be anything.
It could be anything. It could be elephants. It could be anything.
Okay. Okay.
Right? So what do we know? Well, right, we give an algorithm for the algorithm problem using an algorithm for the oracle problem. And here's some various cases, right? What happens if it turns out that there is an algorithm for the oracle problem? What do we learn?
So I guess the algorithm for the oracle problem solves the PO. Yeah.
Yeah. Right? Right? Here we're saying I give you an algorithm for the algorithm problem, given I have an algorithm for the oracle problem, right? So if I do have an algorithm for the oracle problem, then I do have an algorithm for the algorithm problem, right? On the other hand, suppose the counterpositive, if there's not an algorithm for the algorithm problem, then there's not an algorithm for the oracle problem, right? Those are the things that we're proving.
Yes.
Right? What about this over here? Suppose that there is an algorithm for the algorithm problem. Does that prove us anything about the oracle problem? No, it proves us nothing, right? It could be that the algorithm for the algorithm problem has nothing to do with what we just did, right? Similarly, if there's not an algorithm for the oracle problem, that doesn't tell us that there's not an algorithm for the algorithm problem. It just tells us that we have to get it some other way, right? All right, so these are just our conclusions, right? Our conclusion is that P algorithm is at least as easy as the oracle problem, because if we can do the oracle problem, we can do the algorithm problem, right? Or the oracle problem is at least as hard as the algorithm problem, and we write it down like this, right? Everybody good with that?
Can we like think about this as like an if statement? Like if this works, then this works?
Yeah.
Yeah.
That's up here. Up here it says, if we have an algorithm for the oracle problem, then we have an algorithm for the algorithm problem.
Okay.
Right?
Like if A, then B. Okay.
Yeah. Right? And why do we put the little subcomputable here? Is just like, well, my algorithm here, what's the running time of this algorithm compared to this algorithm? And generally the running time is really easy, so we don't give it much thought. Right? Now, why do we do this? Well, we might do it to create a new algorithm for a problem we didn't know before, right? Or we might do it to prove that a problem is hard, that we didn't know it was hard before. Or we might do it to prove two problems have similar structure. So for example, you guys haven't done this yet because this is 3101. But in 3101, the third year algorithms, I give an algorithm for solving network flows. And so then I want to marry the boys and the girls off. And how do I determine who to marry off in an optimal way? I take the boys and the girls and I produce a network, and the network gives me an answer, a flow through the network, and that tells me which boys to marry, which girls, right? So, I mean, we didn't do that in this class, but you just know that this is, if I know how to solve one problem, I can use it to solve another problem. All right? So on the other hand, we know that the halting problem is hard, right? So we can use it to prove that other problems are hard. So for example, we know that the halting problem is hard. We prove that saying hi is at least as hard. So we now know that the hi problem is at least as hard as the halting problem, but this problem is undecidable, right? Right? We know that P oracle is undecidable. So by contradiction, assume the oracle problem is decidable. Oh, this is the oracle problem here, the high problem, right? We want to prove that this high problem is undecidable. It's the oracle problem, right? How do we prove it's undecidable? Well, we assume by contradiction we had an algorithm for it. Well, if we had an algorithm for it, then we would have an algorithm for the halting problem, right? But we don't have an algorithm for the halting problem, so we don't have an algorithm for the oracle problem. Same thing we've sort of said before, right? So now we're talking about how to build this instant map, right? Here we're given, right? This is the problem for the high problem. We want to map, here's the input to the halting problem is a Turing machine and an input, and we want to know, does it halt? What's the input to the high problem is a Turing machine and an input, and we want to know if it says high. So we have to do our mapping. And what does our mapping do? It takes this Turing machine, we're given Turing machine M, and we construct a Turing machine that we construct a Turing machine. We sort of remove the halting problem, the halting state, and we add the high state, right? This just over here is saying we don't have to worry about what does the universal Turing machine do? It simulates one Turing machine by another, but we're not actually doing that because we're building M prime, and M prime can actually look like M. Oh, that's the wrong direction, isn't it? We're supposed to be subtracting off the halting that plus that. Did I have that the other way around before, or was that a typo before? I don't remember. Anyway, that definitely should go that direction, right? Have to remember to fix that. All right, everybody kind of follow this, right? Or we write code for it.
Yes, sir.
All right. And we know that M halts an I, even if only if M prime says high. Oh, here's another. I'm changing what we did slightly. All right.
Yeah.
Remember before I gave M prime the same input, right?
Yeah.
But I'm not going to do that anymore. And you will see it doesn't help this problem any, but it's going to help us in the future. All right. So I'm going to do a slightly different thing. I'm going to define M prime. When I define M prime, it's going to be given its own input, right? So we want to know we have to define M prime, right? Oh, when we give the oracle, we could give it the same input I or not. I don't care. But now I'm defining M prime. So I want to know what M prime does on its input I prime. What it's going to do is it's going to completely ignore its own input, right? It's given some input, but we ignore it. And then what we have built into M prime has memorized M and has memorized I. So what M prime does is it runs M on I.
I have a question.
Yeah.
What's the benefit of having like a different input? So you just use I prime here?
Don't worry about it.
Okay.
We'll use it later. Right now, just understand what we're doing. I'm telling you what M prime does. And it takes some input and it ignores its input. All right? It ignores its input and it does what M does on I. All right? So now let's see if everything still works. We want to know, well, what does M do on I? Does it halt or not? Well, you'll note if M halts an I, then what does M prime do on its input? Well, M prime on input, its input is going to say high, no matter what the input is, right? No matter what input you give M prime, whatever input you give M prime, it's going to say high, right? Because it ignores its input, right? What happens if M halts on I?
Then it's not gonna give.
Sorry, if M doesn't halt on I. If M doesn't halt on I, then M prime is going to never say hi. No matter what the input is, it will never say hi. Right?
Yeah, makes sense, sir.
Right? Everybody get that? I just changed it from what we did before so that M prime ignores its input. Right? That's the only change. All right. So now we are going to build our. We're given an oracle that solves the high problem, and we want to design an oracle that solves the halting problem. It's the same as we did before, right? We're given an M and an I, and we want to know, does it halt? So what do? We build M prime, and we give the oracle M prime. We might as well give the oracle the same capital I, same N, I, it doesn't matter, right? We give it M prime. And we want to know what the oracle does. Well, the oracle would say yes or no, based on whether this says hi or not. And what do? We say the same answer, yes or no, right? And so we want to prove that this program works. Well, does it work? Well, if the answer is yes, if M does halt on I, if M halts on I, then M prime says hi on every input, right? So if M, that's what I was saying. If M on I halts, then M prime on I says hi no matter what. So the oracle will say yes no matter what. So we say yes, and we know that we got the right answer, right? But if M prime doesn't halt, then M prime is always going to say is going to give no highs. So then the oracle is going to say no, and we're going to say no, and either way we got the right answer, right? Does that make sense? All right.
Yes, sir.
And that's it. All right. So now I told you that we're going to solve a number of problems, right? So now let's ask this question. I give you a Turing machine M prime, and I want to know, does M prime halt on the empty string, right? I want to prove to you that that problem is undecidable. All right. How are we going to do it? We're going to assume we have an oracle for the halting problem, and I'm going to design for you an algorithm that's, oh, sorry, the other way around. See, I always get it wrong. We're going to assume we have an algorithm for this harder problem, right? If we have an algorithm that solves the halt on this empty string problem, right? We pretend we have an algorithm for that, and we're going to use it to get an algorithm for the halting problem, right? But we know that we don't have an algorithm for the halting problem, so we don't have an algorithm for the does M halt on the empty string problem, right? So how are we going to do this algorithm? Well, actually, it's going to be really easy now. I'm given an M and an I. What do I think I give the oracle?
M prime and I prime?
Well, no, not I prime. I give it the
string.
same M prime,
Oh,
the same M prime
yeah.
I gave before. But I don't have to give it an I, right? Because it doesn't need an I. It just needs an M prime. So I give it the exact same M prime than I did before, right? And what happens here? Well, if M prime, we want to make sure, right? We still have that if M on I halts, then what does M prime do? Well, it says hi, right? We kind of got rid of the fact that it says hi, but it might say hi or might not say hi, but it's simulating it. So it's going to halt for every input, right? Because it's still ignoring its input, right? We're basically doing the same thing we did, but we didn't bother to say hi, right? we ignored the input, we ran M on I. And then if M on I halts, we halt. If M on I runs forever, we run forever. Right? So if M on I halts, then M prime halts for every I prime because it ignores its input. Right? And if M and I doesn't halt, then M prime doesn't halt for every input.
So like we don't have to print anything here. We're just like saying a point, like it's gonna run, right? Like here, like in the previous one, you printed high, right?
Right.
But
right.
here, you don't have to print.
We don't care about high. We care about whether we stop. So this is the same code we had before, except I deleted printing high because we don't care we print high. Right? Okay. So that basically M prime will halt if M halts on I, and M prime will not halt if M doesn't halt on I. Right? But it's still M prime does it for every input. Why? Because we're ignoring the input. Right? Everybody get that?
Yes, sir.
So now let's make sure our algorithm works. Right? It's the same as we had before. Right? The algorithm works. Right? In fact, we care does it halt on the empty string, right? But why does the oracle say yes? We have to stress, why does the oracle say yes? Well, if M halts on I, then M prime halts on every input. So it halts on the empty string. And if it halts on the empty string, the oracle says yes, right? Now, if MI doesn't halt, then M prime doesn't halt for every input. So it doesn't halt for the empty string. So the oracle says no. Right? Here we're just checking here that if M prime halts for every input, then it halts for the empty string. So the oracle says yes. Right? And if M prime halts for no input, then it doesn't halt for the empty string. So the oracle says no. Right?
All right. I guess, so all of this really fancy oracle business aside, technically, this problem is just the halting problem.
Right.
Except we only input the empty string.
Yeah, exactly.
So this is a real trick. That's kind of funny.
Right, exactly.
Cool.
Right. In fact,
that's fun.
Did you guys did you guys get the problem that was on the homework assignment where you needed to find out the bit of my password?
Sir.
Did you guys get that one?
I hope so.
Right?
I think I came up with something pretty clever, but I guess we'll see.
You designed an algorithm that, well, I posted the solutions if you want to look at them. Anyway, let's go on to this. So now we want to know, here's our problem. We want to know, given a Turing machine, does it halt on every input? Right? That's a different question. That's what our oracle is going to do now. It's going to tell you whether or not M prime halts on every input. Well, that's still going to work for us. It's because if M prime halts on every input, the oracle says yes. And if M prime halts on no input, then the oracle is going to say no. And we have the exact same reduction.
So just a question about this reduction,
yeah.
Particularly about the prints high string. So we did a reduction from prints high to halts to show that it's greater or equal to complexity.
Yep.
But the second part, we did a reduction then backwards. So would that then say that they are equivalent complexity classes?
We've never gone the other direction yet.
So when we did that, given M on input I and we ignore I prime, and then we run, I forget what the terms are called now, but we run the prints high machine, right?
Yeah.
And then our machine either prints yes at the end or no at the end instance for M. Would that not be a reduction?
All the reductions we've done have had the halting problem on the easy side. We've always, in every case, we've been coming up with algorithms for the halting problem.
Mm-hmm.
So that always puts the halting problem on the easy side. And so we're always proving things are harder than the halting problem. We've never gone in the other direction. So on your test, you went the other direction. Yeah. On the test, you said, suppose I have an algorithm for the halting problem. Come up with an algorithm for finding the ith bit of Jeff's password.
Yes, exactly.
Right. So there you did a reduction the other direction.
So for curiosity's sake here, could we go in other direction?
Oh, yeah,
for
sure.
that question? Okay,
for
so
sure.
the equivalent complexity classes.
For sure.
Right?
In fact, yeah. If you can solve the halting problem, you can easily solve all of these problems.
Okay, gotcha.
Right?
Just wanted to confirm that.
In fact, you do it the same way we did on the assignment.
Okay,
right?
Thank you.
All right, so here's another one. Our oracle now tells us, given an M prime, does it halt on some input, right? Well, that's exactly the same will happen, right? Because if M prime halts for every input, then it halts for some input. So the oracle will say, yes. And if M prime halts for no input, then the oracle, it doesn't halt for some input. So the oracle will say no, right? So you see how by having this, you ask, why did I ignore my input? And the reason I got M prime to ignore its input is we checked off a lot of good problems here really quickly, right? So here's another one. The input to the Turing machine now, the input to the oracle now is, I give you the description of 2 Turing machines, and I want to know, do they give the same answer or not? All right. So what am I going to give it? I'm going to give it 2 Turing machines, M prime and M double prime, right? And I need to tell the oracle the algorithm for both of them. Well, my M prime will be exactly what I always do, right? It's the same M prime as always. It's designing it from M and I. But what's M double prime going to do? M double prime is a really easy algorithm, Turing machine. All as it does is it ignores its input, and it, no matter what, it stops and accepts, right? People see that? So here I'm given M and I, and I want to know, does M halt on I? So I designed 2 Turing machines. I designed the M prime like I did before, and I designed a fixed Turing machine called M double prime. And what M double prime does is it halts and accepts, right? So then let's see whether or not our algorithm works. Well, if M on I halts, then M prime halts for every input. What does M prime do? Double prime do. M double prime halts for every input. Oh, look at our M prime and our M double prime doing the exact same thing. So what's our oracle going to do? It's going to say yes, and we're going to say yes, right? Let's look at the other case. If M and I doesn't halt, then what does M prime do? It never halts. Do they do the same thing? No, M prime and M double prime do very different things. So the oracle is going to say no, and our algorithm works. Right? Everybody getting that?
Yeah.
All right, so now we're going to do the harder problem, all right? So we're going to spend some more time on it, but count on this being harder, all right? All right, so what is our problem again, right? I'm given the oracle, the problem is you give the oracle an M prime, you give it a Turing machine, right? And let's define L to be the set of strings on which M prime halts, right? So it's a language. It's the language of strings on which M prime halts. And then we ask, is that language computed by a regular expression? Is it computed by a DFA? Yes or no? So it's that's kind of a weird problem, isn't it? Everybody understand what the problem is? All right, so here, let's see how we're going to do it, right? I'm given a Turing machine, an M and an I. I'm going to produce some other algorithm here. I'm going to produce some machine. Well, we're going to just try this machine and see if it works, right? It won't work, but let's see if it works. Let's give it the same M prime and see what it does. Well, if we give it the same M prime, what does M prime do? M prime halts on every input. So what is L? L is the everything language, right? It halts on everything. So L is the everything language. Is the everything language, is that regular? Yeah.
Yeah.
Right? That's easy, right? So the oracle says yes, right?
Oh, but the second one now will be.
Yeah. So now if M on I doesn't halt, then the language is the nothing language, right?
Empty.
The nothing language is also regular. So the oracle also says yes, right? So we haven't been discerning. We haven't figured out whether M halts on I or not, right? Everybody see that?
Yeah. Yeah.
Right? Everybody gets that if M halts on I, then M prime halts on every I prime. So what is the language of M prime? It's the everything. It accepts everything. It halts on everything. Well, the everything language is regular. In fact, I just gave you a regular expression for it. 0, 1 star is a regular expression. So the oracle says yes, right? On the other hand, if M on I doesn't halt, then M prime doesn't halt on every input.
So like it doesn't matter. It doesn't matter if it halts or not.
Yeah, so what's the language? What's the language of M prime? It accepts nothing, right?
Yeah.
So it's the empty language. Well, that's also regular. So the oracle also says yes. Right? People get that? All right, so that doesn't work. And so we have to do something harder. All right?
Oh.
So I'm given a Turing machine M and an I, and I want to know whether it halts. And I have to map it over to Turing machines that might do regular languages and might not do regular languages. All right? So let's look at here. That dot is a particular Turing machine, right? M prime, the input to this problem is a Turing machine. So I can ask that particular Turing machine, well, what is its language? On some inputs, it says yes, and then some inputs, it says no, and on some inputs, it runs forever, right? So let's look at in fact here, yeah, so there's, all right, so I haven't yet, yeah. So here, what about a no instance, right? This guy here is a no instance. Because it's a no instance, we know it has no regular expression, right? I mean, it has no Turing DFA that does it. But still, on some inputs it says yes, on some inputs it says no, and in some inputs it runs forever, right? But we want to be more interesting. I'm going to split up the world into more types of Turing machines, all right? More discerning. Here I've talked about different types of Turing machines, all right? Let's first talk about Turing machines up here. this is the set of all Turing machines who say yes on 0 to the n, 1 to the n. All right? If the input, if this Turing machine, what does this Turing machine do? If the input is of the form 0 to 1 to 0 to the n, 1 to the n, it says yes. Right? And if the input's of some different form, like 1, 0, then it says no. Right? Everybody get this is a set of Turing machines whose language is 0 to the n, 1 to the n. And I know that those Turing machines are no instances. Why? Because we know that there's 0 to the n, 1 to the n is not regular. Right? Does that make sense?
Like, are you saying, like, if there is no instances, we go to this part of the world. If there is instances, we go to this part of the world. And you're trying to split them to contain all of the options?
Yeah, let's not get carried away thinking about too much. Let's just think about that Turing machine right there. Right?
Yeah.
Or any Turing machine in this little region. What does that Turing machine do? Well, if it's given an input of the form 0 to the n, 1 to the n, it's going to stop and say yes. If it's given an input of any other form, it's going to
stop and say no.
No, it probably won't stop. It might stop and say no. Probably what it'll do is run forever.
Oh.
All right. So the question is, well, what's the language of this machine? Well, the language of the machine is then the L of this machine is 0 to the n, 1 to the n. Why? Because those are the inputs to which it halts and says yes. Right? The other inputs, it doesn't halt and say yes. So those are no instances. So what's the language of this machine? The language of this machine is 0 to the n, 1 to the n. Well, is that regular? No. Right? That's what we're saying. The language of this machine is 0 to the n, 1 to the n, which is not regular. And that's why this machine, what would the oracle say for this machine? The oracle would say no for this machine. Right? Does that make sense?
Is it no because it's not regular?
Because it's not regular, right? This is a Turing machine whose language is 0 to the n, right? Remember, we need the oracle to say no, right? At some point, the oracle has to say no, or else it's not discerning. So at some point, we have to give it an input for which it will say no. And I'm just saying this is a Turing machine. My Turing machine here, what it does is it decides whether the input 0 to the n, 1 to the n. And so its language is 0 to the n, 1 to the n. So its language is not regular, and hence the oracle will say no for it. Right? There are many Turing machines that do that. All right. So here's another type of Turing machine, right? These Turing machines down here, they compute 1 to the n, 0 to the n, right? So the first type up here compute 0 to the n, 1 to the n. And the ones, what are we saying here?
So right. Here it does not care.
It just doesn't care. That's all it was. We're just saying it doesn't care. All right, so anyway, let's go over to these ones. What does this Turing machine do? We're calling it the all Turing machine because what it does is it halts on everything, right? The language of this machine is the everything language, and the everything language is regular, so it's a yes instance for our oracle.
Yeah.
Right? Everybody follow? We're just finding different types of inputs to the oracle and what the oracle would say. I'm just saying this type of input, the oracle will say yes, and this type of input, the oracle will say no. Right?
Sir, so would the order matters? Like when you said on the right top, you said there is a Turing machine for 1 to the n and 0 to the n.
Yep.
On the left, they said 0 to the n and 1 to the n.
Yeah.
And you just said that does not matter. Like
Well,
in the page before.
I'm just saying there are lots of different Turing machines out there, right?
Oh, okay.
And I'm just telling you different types of Turing machines, right? There are Turing machines that say yes to 1 to the n, 0 to the n, their language. But we're going to ignore those guys. And there's Turing machines that always say no, and we're going to ignore those guys, right?
Okay.
All right, so now we need to come up with an instance mapping, right? For every m and I, we need to map it over to some Turing machine, right? And what we're going to do is when m halts on I, we're going to map it to Turing machines that always say yes. And when m doesn't halt on I, we're going to map it over to a Turing machine whose language is 0 to the n, 1 to the n.
Yeah, yeah.
Right? Does that make sense? That's what we need to design our Turing machine to do. Right? Because these inputs, it's going to map to a no instance. The Oracle is going to say no, so we're going to say no. And on these inputs, it's going to map to a yes instance. So the Oracle is going to say yes, and so we're going to say yes. Right? Everybody good with that? How are you doing, Oriana? You getting that?
Yes, I am. Thank you.
Excellent. All right. So that's the type of, right? It's our instance map, right? We don't have to map to every type of Turing machine. We only map to Turing machines that we care about. So we're going to decide to map to these types of Turing machines and to those types of Turing machines. And we're never going to map to any other type of Turing machine. And that's our choice, right? All right. So now we have to come up with code, all right? Given m and I have to come up with code for m prime, right? So given m and I build code m prime. So let me tell you what the code for m prime does. Here's m prime. It's given an input I prime. What does m prime do? Well, if I prime has the form 0 to the n, 1 to the m, then it's going to automatically halt and accept, right? If I prime doesn't have this form, if it has any other form, then what we're going to do is we're not going to halt and accept right away. What we're going to do is we're going to run m on I. And if m on I halts, then we're going to halt as well. But if m and I runs forever, then we're going to run forever. All right? That's just code. I'm giving you code for m prime, right? You gave me code for m. I give you code for m prime. All right? So now let's think about what happens. Right? There are two cases. Suppose m and I halts. What does my Turing machine do? Well, if m on prime halts, well, if I has this form, right? If I prime has this form, what does m prime do? It halts, right? Right. I'm just trying to figure out, this is a case, assume m halts on I. What does m prime do? Right? Well, there are various cases. First case, if its input has the form 0 to the 1, is it 0 to the n, 1 to the n, then clearly m prime halts and accepts, right? Here's another case. What happens if m prime has the form 0 to the 1 to the n, 0 to the n? What does the code do? Well, it doesn't have this form. So it comes down here and it runs m on I, right? What does m on I do? Oh, m on I doesn't halt. Sorry, the wrong case. Here, m on I doesn't halt, right? So we come down here and what does m on I do? It doesn't halt, right? So what does m prime do? M prime runs forever, right? All right. What happens if m prime has any form other than 0 to the n, 1 to the n? It comes down here. and M prime runs forever. Right? Does that make sense? So what's the language of M prime? The language of M prime is 0 to the n, 1 to the n. Right? Right? M prime says yes to inputs of the form 0 to the n, 1 to the m, and it runs forever on every other type of input. So what's the language of M prime? The language of M prime is 0 to the n, 1 to the n. Right? Everybody get that? All right, right? Now here I'm just saying a little caveat. M prime recognizes 0 to the n, 1 to the n. It doesn't compute it because it doesn't halt. So it's the difference between recognizing and computing, deciding, but let's ignore that. Anyway, the point is that the language is 0 to the n, 1 to the n, and that's not regular, right? All right, so now let's go over to the case that M does halt. If M does halt, what does it do on inputs of the form 0 to the n, 1 to the n? Well, it halts and accepts them. What does it do on any input that doesn't have that form? Well, it runs M on I. M on I does halt, and then it halts. So it accepts them, right? M prime is accepting every input. So what's the language of M prime? It's the everything language. Is the everything language regular? Yes, right? So M prime, the language of M prime is regular. Everybody following that? All right, so let's put all the pieces together. What do we have? We have that if M on I halts, then the language of M prime is regular. And if M on I doesn't halt, then the language of M prime is not regular, right? So now let's build our oracle, right? We have an oracle that solves the regular problem, and we need to build an oracle that solves the halting problem. So we're given an M and an I, and we want to know, does M halt on I? What do? We build this funny program, M prime, right? Just like we did before. And what does the oracle do? The oracle says yes or no. What do? We say yes or no, right? And now we must prove that this algorithm works. Well, the first case is what happens if M and I halts. What do we want to do then? We want to say yes, right? So let's see what we do. If an M and I halts, then M prime is regular. If M prime is regular, then the oracle is going to say yes, right? And if the oracle says yes, we say yes. And so the algorithm is giving the right answer, right? So now suppose M and I doesn't halt. If M and I doesn't halt, then M prime is not regular. If M prime is not regular, right? M prime is going to have the language 0 to the n, 1 to the n, which is not regular. So the oracle is going to say no. And we're going to say no, and we've solved the problem, right? So each piece I don't think is too hard, but it's a little confusing, right? Because there's the oracle, we have the M algorithm, we have the M prime algorithm, we have the algorithm for the oracle, we have the algorithm for the halting problem. There's all these pieces, so many moving pieces, right? But the bottom line is that I was given an algorithm that solved the regular problem, and I used it to design an algorithm for the halting problem, right? But I can't solve the halting problem, so I can't solve this is it regular problem. All right, does that make sense? And here, if our let's do this one quickly. I'm given an input and I want to know does the oracle says, does my special problem oracle halt on that input? Well, so my input that I give the oracle is simply going to be M and I. I give it a description of M and I. And what's the special Turing machine will be the universal Turing machine, right? So the universal Turing machine will halt if M halts on I, and so the oracle will say yes. All right. I'm running out of time here. Unless people want to do more of this stuff, we can do more of it. There's Rice's theorem, which is kind of hard. And if people humor me, I have another 8 minutes to go into the top of the hour. So let's just talk about some other problems that are different. Here's a domino problem, right? So the input consists of a collection of dominoes, right? And each domino has a string on the top and a string on the bottom, right? That's what each domino is. And what is the solution to the domino problem? It's you can string together as many dominoes as you want. Oh, there's a finite set of collection of dominoes, right? Each domino has a string on the top and then a string on the bottom, but you can repeat. You can use the same domino many, many times. You have infinite copies, unbounded number of copies of each domino. So the question is, can I build a sequence of these dominoes such that what? Such that if you look at the total string on the top, right, the total string on the top is A, B, C, A, B, C. What's the string on the bottom? A, B, C, A, B, C, right? It's the same string on the top and on the bottom, right? So can you do that? Well, it turns out that that is undecidable. And we build it, the Turing machine. So the state of the Turing machine is there, right? Here we have what is the contents of the Turing machine tape, and are we transitioning from is the head moving, right? We're not going to, right? So we do that reduction. Here's another interesting one, right? I give you a fixed set of tiles, right? So there's a tile of this shape and a tile of this shape. And there's many copies of each tile as you want. And you want to know, can I build a square out of them with you can rotate, oh, you can't rotate the pieces, and you can repeat the pieces as often as you want, right? So again, that's undecidable. And how we do it is we encode here the description of the Turing machine at each point in time. And we say, if M halts on I, then you can build, you can put together to make a square. And if M doesn't halt on I, you can't. Here's another cool problem. Oh, here's some fun. I give you a context-free grammar, and I want to know, does that context-free grammar generate some given input I? That's parsing, right? Given a grammar, can I parse it? You can do that in N-cube time. Given a grammar, does it generate every string? That's undecidable. Does it generate no string? I can give you an algorithm where it does that in N-time. Given two grammars, do they generate the same language? Again, that's undecidable. Here's an this is just the reduction, and we don't want to do the reduction. It's all back to the Turing machines, right? Oh, here's the game of life. Have you guys seen the game of life?
Nope.
This was very popular when computers were first invented, because now you have fancier video games. But here's the game of life, is you have an infinite square of cells, and at every point in time, a cell is either alive or it's dead, right? And if it's live, it's black, and if it's dead, it's white, right? And then there's some simple rules. right? For every living cell, you count how many neighbors do I have that are alive. And if the number of neighbors is 2 or 3, then you live. And if the number of neighbors is not 2 or 3, then you die, right? Here's another point. But if you're a dead neighbor, you ask how many neighbors are alive. And if the number of neighbors you have is 3, then you come alive, right? So you can just set up simple rule. Oh, so then there's a starting configuration, right? So in this starting configuration, it doesn't do anything. If you start in this configuration, you can see how it walks. If you start in this configuration, it toggles back and forth, right? Here's a pretty one. It toggles back and forth, right? Now here's a more complicated thing. If you start with this configuration, then it does this weird pattern, right? Everybody understand that? And so here a question is, if the input is I give you initial configuration, and then you want to ask something about what it does. Does it run forever? Does it die at some point? Does it stop? Right? You just want to ask that. And it turns out that that problem is undecidable. All right? Because basically you're asking, I mean, basically this has enough power to be a Turing machine, right? And so then you can encode, does this thing halt or not? All right, I think I got one more in here. In fact, I think I did this one already with you guys. All right. So the input is a multivariate Turing, is a multivariate polynomial. So there, what's a multivariate polynomial? You have multiple variables. Here we have X, Y, and Z, and it's a polynomial in those variables, right? And I want to know if I wanted to know, is there a real solution? Then the way I would do it is I would use calculus, right? And I could find a real solution. In fact, if you found any solution that had a positive number and any solution that had a negative number, then there's got to be an integer. There has to be a solution in between, right? But we're asking, are there integer values for which this gives me 0? And I actually have a book. Oh, no, I don't. I used to have a book that gave a proof of this, but some graduate student borrowed it and never gave it back. So I got an electronic copy from the author. All right. So this says if the variable is real, then you could use calculus, right? But if the inputs are integers, then it's undecidable. Right? You could say, well, I could just try different integers until I find a solution that works, right? And if you found a solution, that's great, right? You just try integers. If you find a solution, that's great. But if you don't find a set of integers, then you don't know. Maybe there's larger and larger integers that give you a solution. And so it's undecidable, right? This was a question that Turing and his advisor Hilbert asked, but people didn't manage to come up with the proof for it until my lifetime. It was somewhat. Maybe I was in high school when they proved this. Anyway, I did manage to read the proof, but it took me about an hour to understand it, so we won't do the proof. And that is the end of the slides. All right.